When an industrial control system fails, the damage is measured in damaged machinery and immediate financial loss. Unplanned downtime in the automotive sector now costs manufacturers more than $2 million for every hour lost. Securing these environments requires monitoring billions of connected devices across an expanding industrial IoT attack surface. Hardening each device and manually tracking anomalous sensor data across that footprint is mathematically impossible. Engineering teams are turning to agentic AI to bridge this gap. By equipping large language models with Retrieval Augmented Generation, or RAG, these systems can ingest complex operational manuals and automatically formulate responses to system anomalies. But giving a text generation engine direct authority over heavy machinery introduces a massive, unacceptable liability. Cyber-physical systems require absolute, deterministic physical control. LLMs are probabilistic text generators that guess the mathematically likely next token in a sequence. A hallucinated response in a medical chatbot provides incorrect information. A hallucinated command in a water treatment plant, like opening a fill valve when a tank is already overflowing, forces a system past its physical limits until it bursts under the pressure. This presents a rigid engineering paradox. We need the semantic reasoning capabilities of an LLM to parse complex manuals, but we cannot accept the physical risks of probabilistic hallucinations. Researchers at Texas Tech and Johns Hopkins universities have designed a solution, the Neuro-Agentic Control framework. This architecture explicitly separates semantic reasoning from physical control. The system isolates the problem into two distinct engines. The LLM, Gemini 2.5 Flashlight, acts as the semantic architect. A pre-trained time series foundation model called TimesFM acts as the numerical sentinel. This dual-agent architecture forces the LLM to operate as a supervised planner rather than a direct controller. Every semantic proposal must be mathematically validated by the physics engine before any hardware moves. We model this paradigm as a system tuple with three elements: state history, semantic actions, and the prediction function. Unlike traditional static equations, this prediction function utilizes TimesFM, pre-trained on 100 billion data points, to capture complex temporal dynamics. The system operates first in a passive monitoring state. The TimesFM Sentinel continuously analyzes the 720 most recent time steps to forecast the next 24 steps into the future. It only triggers an active control state if the forecasted peak exceeds a predefined critical safety threshold, indicating an impending failure. Until that specific threshold is crossed, the LLM remains dormant. The system stays isolated from probabilistic text generation until an anomaly requires a semantic intervention. This architecture details the transition from the anomaly detection loop into the active strategy formulation phase. Once triggered, the Gemini architect receives a prompt with RAG context, including sensor trends, time-to-failure estimates, and physical operating constraints. The architect is strictly forbidden from outputting conversational text. It must generate multiple candidate intervention strategies, formatted purely as a JSON array. Each JSON object contains a precise control vector: the action type, the magnitude, dictating the negative drain rate, and the duration in integer time steps. An initial feasibility filter scans these outputs. If the LLM proposes an action that exceeds actuator bounds, like an excessive flow rate, the system rejects it immediately. A perfectly formatted JSON object is just probabilistic text. The system translates it into a physical simulation to prove it will safely resolve the anomaly. This illustrates Counterfactual Physics Injection. Because TimesFM's weights are frozen, the LLM's command is simulated directly within the forecast. A linear injection bends the trajectory downward based on the proposed drain rate, then caps the offset, locking in the newly drained safe water level. This creates a deterministic projection, showing exactly how the physical system will behave if the semantic command is executed. The final control decision is then determined by an optimization protocol that selects the action resulting in the lowest projected peak risk. If the simulated forecast reveals the strategy causes the water level to exceed the baseline, the system flags it as a hallucination and blocks execution. This linear injection mechanism mathematically guarantees that unsafe semantic proposals are caught and discarded before they can cross the air gap into deterministic physical actuation. To test this architecture, researchers deployed it against the secure water treatment dataset, subjecting the system to complex stochastic cyberattacks. The trials covered 3 specific failure modes injected into the control loops: rapid 150 mm sudden spikes, gradual 100 mm drifts over extended periods, and high noise sensor corruption. The Neuro-Agentic loop prevented breaches in 33.3% of scenarios, outperforming TCN at 13.3% and LSTM at 26.7%. During severe, sudden spikes, the Sentinel achieved a maximum risk reduction of over 215 units, pulling the mitigated peak significantly lower than either baseline. The baseline LSTM and TCN models underperformed because they repeatedly triggered the exact same rigid emergency drain response, lacking the capacity to adjust magnitude and duration based on the specific attack profile. By combining a foundation model with an LLM, the architecture dynamically adapts its mitigation strategies, yielding a higher rate of quantitative risk reduction than traditional deep learning controls. Across all 15 stochastic trials, the system executed exactly 0 physically invalid or hallucinated actions. The LLM did make critical errors. During testing, the semantic architect occasionally produced positive magnitude vectors, proposing to add water to a tank that was already overflowing. This is the Sentinel effect in action. The TimesFM forecasters simulated those defective commands, predicted the resulting accelerated failure curve, and deterministically rejected them until the LLM produced a valid negative magnitude drain vector. This level of verifiable safety requires an operational trade-off. Executing the control loop introduces an inference latency of 1.5 to 2.5 seconds. This delay is too slow for microsecond electrical grid switching, but highly viable for the slower time constants of chemical processing. By decoupling semantic generation from physical simulation, the Neuro-Agentic framework strips the danger from probabilistic text generation, turning opaque LLMs into mathematically verified planners for high-stakes industrial control.